Okay, we are in the section on simple pendulums. So let me kind of sketch this out. Imagine you have something like the roof, and then you take a wire, a nice thin wire, you connect to it, and you have a mass hanging down from there. Alright, some other things we'll want to know will be an angle of release. So simple pendulums are kind of the torque equivalent of the mass on spring. So mass on spring uses force. Simple pendulum uses torque. So we're actually going to get the same kind of relationship, but it's going to look, well, it's going to look different because we are going to have to use torque in the end to get the result we want. We are going to find eventually the same differential equation, just with a theta where we had an x before, and an alpha where we had the acceleration a. So let's think about the forces that would be acting on this, because we'll use the forces to figure out what the torques are. So we have a tension and we have a gravitational force, and those are the only forces that actually act on our little mass making up our pendulum. Now, they can't both produce torque, or at least depends on where you put your center of rotation. Let's put the center of rotation right here. So we'll imagine it's going to oscillate back and forth around that point. Makes sense. So that means we want to find the torque around that point. So torque due to anything. Well, the size of the torque is really found as r cross f, but if we only care about magnitude, then that's just going to be r times f times sine of the angle between them. Okay, well, the important thing to point out here is if we're looking for the torque due to the tension, then it's going to be the whole length of our rod that matters. So we'll have L, we'll have the size of our tension force, and we will have sine of, we start out coming out, we turn around and we go back. They are 180 degrees away from each other. We get zero torque. So the tension can create no torque around our light blue pivot point up at the top. Gravitation, on the other hand, it's going to be L and mg. And if we look at the angle between, it's actually the same thing as the angle theta that we're tilted at. So we'll get an mg sine theta, and it will actually vary as things move back and forth. Technically, there's also a minus sign here if we're worried about directionality of it. Remember that torques are positive when they go in a particular direction and negative when they go in the other. In this case, notice that when we are moved in the positive theta direction, we actually will get a torque due to gravitation that's in the negative direction. So the minus sign is indicating it's opposite the theta. Okay. Alright, so that's a start. I said this was going to be torque. That means we're going to look at the sum of torques is equal to I alpha, which you might remember from your past. And chapter 10, 11, 12. In this case, we've got just the one torque, so we have a minus L times m times g sine of theta. And that's equal to I times alpha. Now, the thing that makes this a simple pendulum is that we can treat it as a point mass. So that means we need to figure out what I is for a point mass. And it turns out that's actually relatively easy. The way you figure out what a moment of inertia is it's the integral of the distance squared with the mass. And in this case, since all the mass is 1 point, it just ends up being r squared times m. Or, more to the point, L squared times the mass. Okay. So minus L mg sine theta is equal to L squared m alpha. Can cancel out the mass and one of the L's. We can rearrange everything to the same side, so we'll get L times alpha plus g sine theta is equal to 0. And one more rearrangement step. Alpha plus g over L sine theta is equal to 0. So close and yet so far. We're really looking for something that has a form like a times some constants, a plus some constants times x is equal to 0. And if it weren't for that sign, we'd actually be there. So this is where we get the one change that's true for pendulums relative to masses on springs. If theta is small, then we get sine theta is about the same as theta. Technically only in radians. Okay. This is why pendulums always talk about small angle of release. So as long as we have a small angle of release, misspelled release pretty bad. Pardon me. So only if the angle is small will sine theta be approximately the same thing as theta, which lets us write alpha plus g over L theta is equal to 0. This now looks basically the same as our previous differential equation and means that theta is going to go as some kind of, well, theta naught is probably a bad thing. Call it an theta amplitude. Cosine of omega t plus a phase. And by analogy with what we've done before, we can actually already see that omega should look like the square root of g over L. Okay. So that's what we get for simple pendulums. I'll actually make a duplicate of this part and we'll summarize at the bottom here. And I'll delete that when I copy it. Copy. Paste, move it down so there's plenty of space around it. Alright. So what have we got? Well, we don't need anything about that to talk about it. Get rid of some of this, some of that. Don't need to talk about the theta angle particularly. Alright, so what do we know? Well, if we have a simple pendulum, the sum of torques will be equal to r minus Lmg theta will be equal to L squared m alpha. Oops, that's a terrible alpha. If theta is small. Small angle of release or small displacements. Okay, that results in alpha plus g over L theta is equal to 0, which gives us theta is some amplitude, cosine of omega t plus the phase, where omega must be the square root of g over L. Last thing to finish this up, since omega is 2 pi over t, that means we also have found the period. And we find for small angle of release, it only depends on the length. Okay, so that wraps this one up. You don't have to know how to solve the differential equation, but you should know how to find the omega. Remember, the way you do that is you'd find the second derivative of theta with respect to time, and you would substitute in back into this equation here, and it will come out quite naturally. You'll basically get minus omega squared plus g over L is equal to 0, which will give you your omega. Alright, that's the end of simple pendulums. We're going to do a practice problem next, and then we'll be going on to physical pendulums, which get a little bit more interesting.